concerns regarding the receptacle voltage drop ordinance are valid. When discussing voltage drop limits, the ordinance may be based on the assumption that the maximum load on a 15-amp receptacle is 15 amps. However, the National Electrical Code, or NEC, allows for a maximum load of 12 amps on a 15-amp receptacle according to Section 210.21 TOR. This means that the ordinance's voltage drop limit may be overly restrictive. Meter accuracy is also a concern. The meter used to measure voltage drop should be calibrated to accurately measure voltage drop in the range of 0 to 2 volts. If the meter is not calibrated, it may overestimate or underestimate the voltage drop. The distance from the receptacle to the utility transformer can also affect the voltage drop. The longer the distance, the greater the voltage drop. The ordinance should take into account the distance to the transformer when setting the voltage drop limit. To address these concerns, firstly, review the ordinance carefully to determine if it specifically addresses the maximum load on a 15-amp receptacle. If it does not, request an amendment to the ordinance to clarify this issue. Secondly, ensure that the meter used to measure the voltage drop is calibrated and accurate. Thirdly, request that the ordinance take into account the distance from the receptacle to the utility transformer when setting the voltage drop limit. If necessary, consult with a qualified electrician or engineer to evaluate the voltage drop in your specific situation. By addressing these concerns, the receptacle voltage drop ordinance can be fair and reasonable. In more detail, voltage drop is the decrease of electrical potential along a conductor through which current is flowing. This phenomenon is a crucial consideration in electrical system design and operation, as excessive voltage drop can lead to inefficient performance, overheating, and even equipment failure. The NEC provides guidelines and recommendations to manage voltage drop effectively, ensuring safe and reliable electrical installations. The NEC recommends that the voltage drop on feeder and branch circuits should not exceed 3% for power, heating and lighting loads, or a maximum of 5% for feeders plus branch circuits. These limits are not mandatory but serve as a benchmark for good design practice. Adhering to these guidelines helps maintain optimal voltage levels at the point of utilization, ensuring that equipment operates within its design parameters. Several factors influence voltage drop in electrical circuits. These include the conductor's length, the current flowing through it, the conductor's resistance, and the power factor of the load. Longer conductors exhibit greater voltage drop due to increased resistance. Higher current levels also exacerbate voltage drop, as more energy is dissipated along the conductor's length. The conductor's resistance, which depends on its material and cross-sectional area, directly affects the voltage drop. Conductors with lower resistance, such as copper or aluminum with larger cross-sectional areas, minimize voltage drop. The power factor of the load also plays a role. Inductive loads, such as motors and transformers, have lower power factors, leading to increased current draw and consequently, higher voltage drop. To mitigate voltage drop, several strategies can be employed. Firstly, using conductors with larger cross-sectional areas reduces resistance and minimizes voltage drop. Secondly, shortening the length of the circuit reduces the overall resistance and voltage drop. Thirdly, using conductors with higher conductivity, such as copper instead of aluminum, can also lower resistance. Fourthly, improving the power factor of the load, often through the use of power factor correction capacitors, reduces the current draw and voltage drop. Additionally, ensuring proper connections and minimizing the number of connections in the circuit can help reduce voltage drop. When calculating voltage drop, the following formula is commonly used: voltage drop equals current times resistance. For alternating current circuits, the formula is modified to include the power factor voltage drop equals current times resistance times power factor times the square root of 3. The resistance value used in these calculations should be the conductor's alternating current resistance, which takes into account the skin effect and proximity effect. Online voltage drop calculators and software tools can simplify these calculations, providing accurate results for various circuit configurations and load conditions. Voltage drop is a critical consideration in electrical system design and operation. Adhering to the NEC recommendations and employing appropriate mitigation strategies helps ensure safe, reliable, and efficient electrical installations. The implications of excessive voltage drop can range from reduced equipment performance to potential safety hazards. Therefore, understanding the factors that influence voltage drop and implementing effective countermeasures is essential for all electrical professionals. The National Electrical Code provides specific guidelines for sizing conductors to limit voltage drop. These guidelines are not mandatory but are recommended to ensure optimal performance of electrical equipment. The NEC recommends that the voltage drop on feeder and branch circuits should not exceed 3% for power, heating, and lighting loads, or a maximum of 5% for feeders plus branch circuits combined. These recommendations are found in Informational Note No. 1 to NEC Section 215.2 A for feeders and Informational Note No. 1 to NEC Section 210.19 A for branch circuits. To determine the appropriate conductor size, electricians and engineers use voltage drop formulas and tables provided in the NEC and other industry resources. These tools help calculate the expected voltage drop based on the circuit length, conductor material, ampacity, and load characteristics. The voltage drop formula for a single-phase circuit is voltage drop equals 2 times K times Q times I times D, divided by circular mils, where K is the direct current resistance for the conductor material. Q is 1.0 for direct current or single-phase circuits, I is the load current in amps, D is the one-way distance in feet, and circular mils is the conductor area. For a three-phase circuit, the formula is voltage drop equals the square root of 3 times K times Q times I times D, divided by circular mils, where Q is 0.866 for three-phase circuits. The NEC provides tables such as Table 8 in Chapter 9 that list the direct current resistance values for different conductor materials. These values are used in the voltage drop formulas to calculate the expected voltage drop for a given circuit. Several factors can affect the accuracy of voltage drop calculations. These include variations in conductor temperature, changes in load current, and the presence of harmonics. Higher conductor temperatures increase resistance, leading to greater voltage drop. Fluctuations in load current can also affect voltage drop, as higher currents result in greater voltage drop. Harmonics, which are non-sinusoidal waveforms, can increase the effective current and voltage drop in a circuit. To improve the accuracy of voltage drop calculations, it is important to consider these factors and use appropriate correction factors. The NEC provides guidance on adjusting conductor ampacity for temperature and other conditions, which can help account for these variations. Additionally, using accurate load data and considering the presence of harmonics can improve the accuracy of voltage drop calculations. The NEC provides specific guidelines for voltage drop calculations and conductor sizing to ensure optimal performance of electrical equipment. By following these guidelines and considering the factors that can affect voltage drop, electricians and engineers can design electrical systems that minimize voltage drop and provide reliable power to connected loads. The NEC provides tables and examples that illustrate how to calculate voltage drop and select appropriate conductor sizes. These resources can be helpful for understanding the concepts and applying them in practical situations. Voltage drop is a critical consideration in electrical system design, and the NEC provides valuable guidance on how to manage it effectively. The impact of voltage drop on electrical equipment can be significant, affecting performance, efficiency, and lifespan. When voltage drop exceeds acceptable limits, equipment may not operate as intended, leading to reduced output, increased energy consumption, and potential damage. Motors, for example, are particularly sensitive to voltage drop. Low voltage can cause motors to draw excessive current, leading to overheating and premature failure. Lighting systems can also be affected by voltage drop, resulting in dim or flickering lights. Electronic equipment, such as computers and control systems, may malfunction or shut down completely due to insufficient voltage. In addition to affecting equipment performance, excessive voltage drop can also increase energy consumption. When equipment operates at lower than rated voltage, it may draw more current to compensate, resulting in higher energy bills. This is particularly true for motors, which can become significantly less efficient when operating at reduced voltage. The NEC provides guidelines for acceptable voltage drop limits to minimize these negative impacts. By keeping voltage drop within these limits, electrical systems can operate more efficiently and reliably, extending the lifespan of connected equipment. Regular maintenance and inspection of electrical systems can help identify and address voltage drop issues before they become major problems. Checking conductor connections, inspecting for corrosion, and measuring voltage levels at various points in the circuit can help detect and correct voltage drop issues. Additionally, using appropriate conductor sizes and minimizing circuit lengths can help prevent voltage drop problems in the first place. Voltage drop is a critical consideration in electrical system design and maintenance. By understanding the impacts of voltage drop on electrical equipment and following the NEC guidelines, electricians and engineers can ensure that electrical systems operate efficiently, reliably, and safely. The NEC provides valuable resources and information to help manage voltage drop effectively. Voltage drop can be measured using a variety of tools and techniques. The most common tool for measuring voltage drop is a digital multimeter, which can accurately measure voltage levels at different points in a circuit. To measure voltage drop, the multimeter is connected in parallel with the load or circuit segment being tested. The voltage reading is then compared to the expected voltage to determine the amount of voltage drop. Before measuring voltage drop, it is important to ensure that the circuit is properly loaded and operating under normal conditions. This will provide an accurate representation of the voltage drop that occurs during typical operation. It is also important to use a multimeter that is properly calibrated and has sufficient accuracy for the application. When measuring voltage drop, it is important to take readings at multiple points in the circuit to identify the location of the voltage drop. This can help pinpoint the cause of the voltage drop and determine the appropriate corrective action. For example, if the voltage drop is concentrated at a particular connection or splice, it may indicate a loose or corroded connection. In addition to using a multimeter, other tools can be used to measure voltage drop. These include voltage recorders, which can monitor voltage levels over time, and thermal imagers, which can detect hotspots caused by excessive voltage drop. Voltage recorders can be useful for identifying intermittent voltage drop problems that may not be apparent during a single measurement. Thermal imagers can help locate areas of high resistance or poor connections, which can contribute to voltage drop. After measuring voltage drop, it is important to compare the results to the NEC guidelines to determine if the voltage drop is within acceptable limits. If the voltage drop exceeds these limits, corrective action should be taken to reduce the voltage drop and ensure proper operation of the electrical system. Voltage drop measurements are an essential part of electrical system maintenance and troubleshooting. By accurately measuring voltage drop and comparing the results to industry standards, electricians and engineers can identify and correct voltage drop issues, ensuring that electrical systems operate efficiently, reliably, and safely. The NEC provides valuable information on voltage drop measurement and analysis. To minimize voltage drop in electrical circuits, several strategies can be implemented. These strategies focus on reducing the resistance of the circuit and minimizing the current flowing through it. One of the most effective ways to minimize voltage drop is to use larger conductors. Larger conductors have lower resistance, which reduces the amount of voltage drop for a given current. The NEC provides tables that specify the appropriate conductor size for different ampacities and circuit lengths. Another strategy is to shorten the length of the circuit. Shorter circuits have lower resistance, which also reduces voltage drop. This can be achieved by locating equipment closer to the power source or by using multiple circuits to distribute the load. Using conductors with higher conductivity can also help minimize voltage drop. Copper conductors have higher conductivity than aluminum conductors, which means they have lower resistance for the same size. However, copper conductors are also more expensive than aluminum conductors, so the choice of conductor material should be based on a cost-benefit analysis. Improving the power factor of the load can also reduce voltage drop. Power factor is a measure of how effectively electrical power is being used. Loads with low power factors draw more current than loads with high power factors, which increases voltage drop. Power factor correction capacitors can be used to improve the power factor of the load, reducing the current and voltage drop. Ensuring proper connections and minimizing the number of connections in the circuit can also help minimize voltage drop. Loose or corroded connections can increase resistance and voltage drop. All connections should be made properly and inspected regularly to ensure that they are tight and corrosion-free. Additionally, minimizing the number of connections in the circuit can reduce the overall resistance and voltage drop. Using separate circuits for sensitive equipment can also help minimize the impact of voltage drop. Sensitive equipment, such as computers and electronic devices, may be more susceptible to voltage drop than other types of equipment. By providing separate circuits for these devices, the impact of voltage drop can be minimized. Minimizing voltage drop is an important consideration in electrical system design and maintenance. By implementing these strategies, electricians and engineers can ensure that electrical systems operate efficiently, reliably, and safely. The NEC provides valuable guidance on minimizing voltage drop in electrical circuits. Voltage drop can also be influenced by the type of load connected to the circuit. Different types of loads have different characteristics that can affect the amount of voltage drop. Resistive loads, such as heaters and incandescent lights, have a constant resistance and draw a constant current. The voltage drop in a circuit with a resistive load is directly proportional to the current and the resistance of the circuit. Inductive loads, such as motors and transformers, have a varying resistance and draw a varying current. The voltage drop in a circuit with an inductive load is affected by the power factor of the load. Loads with low power factors draw more current and have higher voltage drop. Capacitive loads, such as capacitors and electronic devices, also have a varying resistance and draw a varying current. The voltage drop in a circuit with a capacitive load is affected by the power factor of the load. Loads with leading power factors can actually reduce voltage drop. Nonlinear loads, such as electronic devices and switching power supplies, draw non-sinusoidal currents that can create harmonics in the circuit. Harmonics can increase voltage drop and can also cause other problems, such as overheating of equipment. The type of load connected to a circuit should be considered when calculating voltage drop and selecting conductor sizes. Different types of loads may require different strategies for minimizing voltage drop. For example, inductive loads may require power factor correction to reduce voltage drop, while nonlinear loads may require harmonic filters to reduce harmonics and voltage drop. The NEC provides guidance on calculating voltage drop for different types of loads and on selecting appropriate conductor sizes for different applications. Understanding the characteristics of different types of loads is essential for designing and maintaining electrical systems that operate efficiently, reliably, and safely. The NEC provides valuable information on voltage drop and load characteristics. Voltage drop is a multifaceted issue in electrical systems that necessitates a comprehensive understanding of its causes, effects, and mitigation strategies. From the initial design phase to ongoing maintenance, addressing voltage drop is essential for ensuring the reliable and efficient operation of electrical equipment. The NEC serves as a crucial resource, providing guidelines, recommendations, and requirements for managing voltage drop effectively. By adhering to these standards and implementing appropriate techniques, electrical professionals can minimize the adverse impacts of voltage drop and create electrical systems that meet the demands of modern technology.